Hello, in this episode of Exploring Rust we're going to take a look at another kind of smart pointer called RefCell. So RefCell is pretty straightforward and simple in essence, but what I did, because just explaining RefCell briefly is really not enough for one video I think, is I tried to write some actual code using RefCell. I'll get into that shortly, but I got into quite a tangle with it and eventually I did manage to finally create a program with a lot of help from Microsoft Copilot that did actually work and does actually demonstrate a possible use of RefCell. But let's start by just taking a look at a simple usage of it. So actually, before I forget, I'm going to put in this allow unused. Always forget about this and it always clutters up my error messages with unused variable warnings and unused functions. Okay, so I'm going to use standard cell RefCell with a capital C there, and then we should be able to make use of that. So this works a little bit similarly to RC, the reference counter, which we saw in the last video. Let's say something like I'll just call it C equals ref, and hopefully I've remembered this correctly, RefCell new. And we can supply some value there. So it could be a struct, it could be an integer, whatever you like, basically. Let's put 5 in there. Then to actually print that, and the thing is that the purpose of a RefCell is actually that it implements something called interior mutability. So you can have a immutable reference like this. So this whole thing should be immutable, but RefCell will actually let you acquire a mutable reference and change the contents of the RefCell. So let's say I want to print it for a start. Let's put in some speech marks and the curly brackets. Now to print it, I could do that with a immutable reference. So to get the actual contents of this RefCell, I could do c dot, and it's got two useful methods, at least two. It's got a method called borrow and one called borrow mute, which is kind of self-explanatory. So borrow should give us an immutable reference to whatever contents the RefCell actually holds. Let's do borrow. And since that's a reference, I think I have to dereference it. So let's try that. Now, if I've got this right, which is a big if, that is going to print the value 5. So let's go to the console and do cargo run. Yep, and then we've got the value 5. But we can actually modify what this RefCell is holding, the value that it contains. So let's do something like, so now I want a mutable reference. I'm going to say c.borrow mute. That should give me a mutable reference. Then I should be able to dereference that. And then let's set this to 6 or something. Not sure if that will work, but we'll give it a go. And maybe I could even, well, I'll do that in a second. Let's go back here and see if that works. Yeah, so now it's set to 6. And if I duplicate that, I presume I could put this up here and then we could see that it was originally 5. So if I run that, we've got 5 and then 6. So that's basically what you can do with a RefCell. Now, why would you ever want something like this is a question that certainly occurred to me. And I didn't really feel like I understood the point of it after reading the documentation page. I did slightly skip the example that's in there because it just seemed a bit overly complicated to me. Maybe I should have delved into that more, I don't know. But the documentation seemed to me a bit verbose for my particular taste, and it didn't leave me all that the wiser. So I tried asking Microsoft Copilot what I could do with this, and I think it was from there that I got the advice that you could implement, for example, a binary tree in a way that you can have the same nodes in multiple places and you can also change the contents of the nodes. So remember, if we want some kind of node-based data structure with the same nodes in multiple places, then you can use RC, the reference counter that we saw last time. And each node will only get cleaned up when all the references to it have been dropped. So it kind of implements multiple ownership. The problem is that the contents of an RC are immutable. You can't modify them. But if you make the content of an RC a RefCell, then because of this interior mutability property, you can then modify what the RC contains, which is then within the RefCell, if you see what I mean. And if you don't, hopefully the code that I'm going to try to write will clear it up. So I started trying to implement a binary tree that can have the same nodes in different places. And I ran into all sorts of terrible difficulties. My level of skill with Rust is just still pretty low. This was the first significant piece of coding I've ever really attempted with it. And along the way I realised that I wasn't clear about what I even wanted. For example, if I'm creating a tree with a bunch of nodes and I want the same nodes in different places, one question is, what's going to own the nodes? Because you have to think about what will own the nodes. What's going to own any particular bit of data that you work with? And if I create a bunch of references to nodes right at the start and then start organising them into a tree, the tree then can't have ownership of those nodes unless you use an RC, a reference counter, right at the very start. But then you end up dealing with reference counters in your, for example, main function. And that to me looks a bit messy, because what I would have liked would be a really clean sort of tree API. Now it doesn't seem like there's any way completely around that. It seems like the code that you end up with Rust in these kinds of situations is inherently going to involve calls to borrow, mute or whatever outside of any API you create. I did actually manage to find a way of avoiding that, but it's not so nice. So I don't know, maybe it's just my lack of skill. And a lot of the questions that I put to Copilot resulted in code that wouldn't actually compile. But again, I discovered then there was another problem, which is that if you have a tree with the same nodes in multiple places, surely you're in danger of creating an infinite tree. You know, if I have like a top node like A, and then, whoops, didn't want that. Let's call it A. And then underneath that, you've got B and C. So it's a binary tree, and B and C are both children of A. And then what if you make A a child of, let's say, B? Well, then the node called A, as we can see here, has links to B and C. So then you've got B and C again here, and B has a link to A. And what you've just done is created a tree that's infinite in size as far as I can see. So maybe literally having the same nodes complete with links repeated in a tree isn't the best idea unless you're going to be very careful about it. Anyway, I tried all kinds of different options. I tried to do what I always do. I tried to simplify the problem here. And eventually what I settled on doing was I created a simple kind of linked list structure where you can link nodes together, and I was able to create a sort of triangle where A connects to B, which connects to C, and C connects to A. I think you could have the same nodes repeated in there if you wanted, although I didn't actually try that out. And more importantly, you can change the contents of the nodes. You can change the data they contain, and I implemented that with RefCell. So I'm going to erase this, and I'm going to show you the code that I figured out, which is my first at all significant bit of coding in Rust. And what I ended up doing, although it's not ideal, was I had some structs which I called data, and they actually contain the data. And they're the things that are actually going to get wrapped in a RefCell. And then I have a separate struct which I called connector, which connects them together in whatever way you like. So I think that, for me at least, that was a pretty good exercise in using Rust, and it really kind of underscored how difficult Rust is. But, you know, with practice, all these things eventually become easy, hopefully. There may be exceptions. I don't know if a language like Haskell ever gets easy. It probably does, though. I'd imagine it does. So let's give this a go. In addition to RefCell, I'm going to want to use standard RC, which we used in the last video. That's the reference counter that basically lets us have multiple owners for the same data item. Now I'm going to want to have a struct which will be a kind of node that I use to store some data. Those are the things that I'm going to connect together. So let's say here struct data, and I'll just give it a simple name, which will be a string. I could make this even easier by just using an integer, but I wanted to use a string because it's just a little bit more of a challenge. And of course we could put more data in there if we wanted. Now one thing I want to do is I want to implement drop purely so that I can see when my data items get dropped, when they get cleaned up. So let's say impl drop for data, and I've done this so many times now, I feel pretty comfortable with it. Let's say function drop, and then we want a reference to a mutable self. And in there, I'm just going to ignore that reference, and we're just going to have print line, some speech marks, pair of brackets, and let's put dropped. And I should be able to access the name of the node. So let's just put self.name here. That bit's pretty straightforward, I think. I'm going to check that this does compile, and it doesn't, because that should be either nothing or else a comma. And now, yeah, now it's okay. I'll just clear this and we'll do a quick format. Now I want a new method that allows me to create new data items. So let's say impl data and create some methods in there. I did look into whether it's possible to combine impl blocks, where you've got some of them implementing traits and some of them not doing, and as far as I can tell, it's not possible. Let's have a function new here, like that, and we're going to pass in a name. We're going to set the data in the struct when we create it. Now I discovered that if instead of just making this a plain string, I do this, I write impl into with a capital I, which is a trait, and sort of diamond brackets there, and string. This allows me to pass to new either one of those hard-coded str reference string slices or an actual string object, like quite seamlessly. And I really like that, so I'm going to use that. So we want to create a new data struct here, and I want to say name is, but now the only downside to using that is that to actually get the string from this, we have to do name.into. But apart from that, it works really seamlessly. Could probably even put that all on just one line, but the formatter might not agree with that. Let's take a look. Wow, what's it done there? Oh no, that's actually what I wanted. Okay, good, great. So let's just do cargo run. Got an error. Why? Yeah, because I've either got to specify the return type or else have a semicolon there. Yeah, no, it's fine. But the thing is, I want all my data structs here to be wrapped in a RefCell, because that's how I want to add them into the structure that I'm going to create. So I'm going to say here RefCell : new, and wrap the whole thing in that, like this. But I also want them to have multiple owners, and for that reason I then wrap the RefCell, the purpose of which is just to ensure mutability. I'm going to wrap this in an RC, so RC : new, put the round brackets there, and let's check that this compiles. Yeah, still seems fine. Very good. So RefCell apparently checks borrowing rules at runtime instead of compile time, and it manages to make something mutable that strictly speaking shouldn't be mutable by, I think, using the unsafe keyword in Rust. So it does some stuff that you're not allowed to do in Rust unless you explicitly flag it as unsafe with a special keyword, I suppose, which I haven't used yet. Now I want to return this whole thing. So what would the type of this whole thing actually be? And what we're actually returning is an entity which can have multiple owners because of this, and it's mutable because of this. So let's say that that's the thing that we're going to return. And the return type of it should be, well, we've got an RC, and then diamond brackets, and within there we've got RefCell, and I put diamond brackets in, and within there we've got data. So that's the whole return type. Let's check it. Yeah, now I've actually got to supply a return value. So if I get rid of that semicolon, the last line becomes the return value of the function, and then we can actually compile it. Now I'm going to end up referring to this type over and over again, but I've found that Rust actually has a kind of type alias thing. So I'm going to say, I can put it anywhere actually, but let's say here maybe, type, I'll call it dataref, that's just something I've made up, equals, and it's going to equal all this thing here. So I copy that and put it there. And then instead of all of this, I can simply use dataref. So a dataref, this new type I've defined, is a data node, a data struct, wrapped in a RefCell, wrapped in a reference counter. And that should be fine. Yeah. The other thing I probably will want is some method here for changing the name in data, which is part of what I want to demonstrate. And the fact that we've wrapped it in a RefCell, that's why I should be able to change the name of it ultimately. So let's say function set underscore name. And so we're going to mutate it. So I think I should have a address mutable self thing. It should be mutable. And we'll have a name. And again, I'm going to use this trick so that I can pass any kind of string to this. I'm going to say impler into diamond brackets string. And then setting the name should be really easy. I just do self.name equals name.into to get the actual string out of this into trait thing, which is implemented for string, I suppose. And that should be fine. I'm running it a lot because I'm very uncertain about what I'm doing here. So that's our data object. Let's go to main now and create some of them. So let d1 equal data : new, and I'll give it a name. So I'm going to try spelling out bug, and then I'm going to change it to big. Let's have a B there just for the name of it. We'll have two more of those. I'm going to create a kind of triangle structure, and I'm going to make that U, and this can be G. Now I'm just going to try something which isn't in the notes that I've created. It's not in the program that I initially put together here after a lot of pulling my hair out, but let's just try to print the value in one of these and see how that goes, because that shouldn't be hard. So there I've got my brackets, and let's take D1. Now so it's wrapped in a reference counter, but those seem to work basically transparently as though they weren't there in many situations through the magic of deref coercion, which we've covered before. So I think I just need to worry about the RefCell, and we're going to have to probably call borrow on that. And then we've got a reference, right? But can I directly access name? Not sure. Maybe I need a dereference operator, or maybe not. Let's try this. Yeah, so it actually does print B, and you can see it's saying dropped G, U and B there as well. So that's how you get at name. The only real inconvenience here to wrapping things in this reference counter and the RefCell is simply that I've got to call borrow or borrow mute when I want to access its fields, because I have to get past the RefCell, and that has these methods borrow and borrow mute. Now let's move on to the next stage. What I want is a connector struct which can connect these data nodes together. So I'm going to say struct connector, and we're going to have left. So left is going to be a data ref, and let's also have right, which is going to be a data ref as well. So the fact that the connector and the data are two different structs here means I don't think we could create a tree from this without some further additional work. But of course you can use this to create a singly linked list. Now let's implement some stuff for connector. So I'll say impler connector, and then I want a new function that accepts two of these data nodes and connects them together. So let's say function new, and I'm going to have left. Wait, I want to put that here. I'm going to have left, which is going to be a data ref, and I'm going to have right, which is going to be another data ref. Then all I have to do is create a connector here. This is going to be the return value of this new function, and the left is going to be, well, it's actually going to be left.clone. The reason for the clone is we're not actually creating a copy of the data node. It's just, if you recall from the last video, these reference counters have a method called clone. And when you call it, it just increments the reference count to whatever it's holding on to, in this case a ref cell containing a data, and it gives you a immutable reference to that. So this is going to be, I guess, an immutable reference. So nothing's really being cloned as such. We're just incrementing a reference count. And only when all of these references have been dropped will the underlying data nodes actually get dropped themselves. And similarly, here I can say that should actually be a comma. Write will be write.clone. So of course the left is, what is it? It's the actual field in the connector, whereas this left is referring to that variable. And the same for the right. That's the field name in the connector. It's not this. But this actually is this variable here. So with this, we should already be able to connect nodes together, I think. It does compile right. Oh, it doesn't. Okay, what have I done? Expected. Yeah, so I've got to specify the return type of this. Let's say that the return type is connector. Try again. Yeah, okay, good. Now let's try using the connector to connect nodes together. I'll get rid of this, and I can say let C1 equal connector new, calling the method I've just implemented, and we'll connect D1 to D2. Now the next thing that I actually want to do is I want to connect, so I've connected D1 to D2. I want to connect D2 to D3. But here's the thing. The way I've implemented this new method here on connector, where is it? Here. So those are kind of normal variables. They're actually, what are they? Reference counters. Once I've passed these to this new function, that's then got ownership. The connector's got ownership of these, so I don't think I could then refer to them after that. If I actually did here something like print line, and let's put in this and try to do d1.borrow.name, I don't think that would work anymore now. Let's try it. Yeah, so when we actually do new, the values get moved into the new function, and the connector is then taking ownership of these values, so we can't then refer to them again. So how do I then manage to connect D2 to D3, being as I can no longer refer to D2? And what we need is a method that lets us access the contents of the connector. So let's go up here, and I'm going to say function left, and this is going to get us the left value within the connector. That's going to have a reference to self, which can be immutable. And I'm going to say self.left, and remember that this is a reference counter, so we can clone it to get an immutable reference to it. And what that will actually return will be, well, it's going to be a reference counter. So I suppose we are kind of cloning the reference counter, but that's all we're cloning. We're actually going to create a new reference counter doing this, but it's kind of managing the same object underneath, the way I understand it. And we can think of it as just incrementing the reference count. So the return type of this will actually be data ref again. So it's actually this thing, because I suppose we're technically cloning that, but we're not cloning the underlying data is the important point. So let's copy this, and we'll create one to access the write node like this. So write, and then we should be able to connect more things together. So if I duplicate that, let's call this C2. And now what I want to connect is C1.write, which is this D2. So C1.write, that's the method I've just implemented. And I want to connect that to D3. And then if I duplicate this again, we're going to have C3, and we're going to connect, what's it going to be? It's going to be the rightmost value of D2, D3. We can no longer use D3 itself. So I want to say C2.write, and I want to connect that to, I'm going to connect this back to the beginning. So I'm going to connect D3 to D1. So here I can say, so D1 is C1.left, so C1.left. And what I've done is I've created a circular or kind of a triangular structure with the B node connected to U connected to G, and G connects back to B via these connectors. I think that's all good. Let's try it. Okay, what did I do here? Expected, it's not got a return value. Let's go back up, and I need to get rid of these semicolons so that the last lines here are expressions which become the return values, which are data refs. So let's try again. Okay, now it works. Good. I thought it would, only because I've previously run through this. Now, I can't actually see any of this. You've only got my word for it that we've actually achieved anything here. So what I'd like to do is print this. So I'm going to create a print method so that we can print the contents of connectors. So I suppose we want to go in here, the implementation for the connector, and create a function which I'll call print. So that is going to need a immutable reference to self, the print object in question, and I can use print line here, and I need to print this out in some kind of sensible format. Let's have the thing that we're going to print, and maybe I'll just put a dash in there, and then the thing that we're going to print from the right hand side. And how do I access these? Well, I use self, and I want to access left, but what is that? It's a data ref, which is a reference counter that wraps a ref cell that wraps a data item. So I can ignore the reference counter. Deref coercion will make that kind of transparent, but I have to deal with the ref cell. To get at the data in it, I need to do borrow if I want to do an immutable borrow here. And then finally I can access name. I believe that should work. And now let's put a comma in and try write here. So I think that's it. Let's try printing some of these. So now I can say C1.print, and I can do that for C2 and C3. So C2 and C3, and let's see what we get. Yeah, so we've got B connected to U connected to G, G connected to B. Is that right? Yeah, B connected to U is connected to G, and then G circles back to the beginning, so G is connected to B. So it's kind of circular data structure. And then they all correctly get dropped exactly once, which is what we want. And what I can also do is use my setName method to change the contents of the nodes, which is the real point here of using RefCell. Let's copy all of that and paste it down here. And then in here, I can say, let's say, for example, C2.set. Now, hang on a minute. What did I actually implement? Yeah, I've not implemented any method on connector. How am I going to do this? So I do have a way that I can do it, but that involves another method. But I want to keep this a bit simple with it if possible. So I think here I can probably just do, I want to change, what do I want to change? I want to change, well, it's the right hand side of connector 1 because that connects D1 to D2. I want to change this U to an I. So could I not do C2.write? That gets me the right hand side of it. And now if I want to change it, so I can ignore the RC, the reference counter, and for the ref cell I can do borrow mute, I think, and then on that I can call set name, I believe, and I can change the name to I, like this. Let's try this, see if this works. Yeah, so maybe put in a blank line here, so print ln exclamation mark, just like that. Try that again. I'll do cargo format just to be sure. Cargo run. Yeah, so you can see that I've changed that G to an I, and everything is still connected up just as it was previously. So the structure of it has been preserved and everything's correctly dropped. So that's really what I wanted to show you. In the program that I created, I did go a little bit further, basically because it kind of disturbs me that we're not just doing c2.write.setName. We've got that borrow mute in there, and then to me that feels like we're exposing some of the implementation details here that I'd prefer to hide away. You can totally solve this and hide away the borrow mute just by defining a, for example, set write name on the connector. and then you can just put that code in that method, and you can boil this down to c2.setWriteName I, or whatever you like. But I'll leave that as something for you to try if you're interested. And the bottom line is that, as you can see, by using this combination of a ref cell within a reference counter, then we can deal with things that we want the reference counter for. We can deal with situations where a data object or some kind of object might have multiple owners that should only be cleaned up after all the owners have gone out of scope or have been dropped somehow. We use the reference counter for that. But then by putting a ref cell within the reference counter, we've created a situation where we can actually change the kind of contents here. We can change the object that ultimately the reference counter is holding on to. Otherwise, we wouldn't be able to do that without this ref cell. Something like this would definitely be way simpler in, for example, Java or Python or almost anything else really. Some of the complication arises from the fact that you can't have null pointers in Rust. So I tried things like creating a linked list where instead of doing stuff like this, so instead of having a separate connector, you have like a next method attached to a node, which gets you a link that's within the node itself to the next link. But the problem is, what if the link within the node might not point to anything? Then you're kind of forced to use an option. And if you use an option, then you can't just chain calls to a method called next that's returning an option. You've got to check to see whether the option contains some or none. So some things that would be really simple in almost any other language, but it has to be admitted a lot less safe, become really verbose and kind of tricky in Rust, it seems. Anyway, Rust is definitely doing what it's supposed to do. It's creating very fast, sort of lightweight, efficient code in a way that's extremely safe. It's just actually programming in it. So far I'm finding it can be frustrating, but what I will also say though is it's kind of like it's almost like playing some sort of video game. It's almost like playing Tetris or something. It does give you a little bit of a mental workout, and I'm sure it does get easier with persistence and practice, because a lot of my difficulties here are just coming from the fact that I'm still so unfamiliar with Rust. Anyway, that's it for this week. If you're watching this on YouTube, you can also watch it on blog.caveofprogramming.com, where I'll also put a bit of a write-up, and you can access the code there as well. So until next time, happy coding.